So we're in the physical properties part of the course, and so physical properties of particles is potentially important from a forensic standpoint. Okay, so there's a lot of different kinds of, properties that we look at, but for particles, we typically like to think about size distribution. So, if you look at sea sand or soil, clay or whatever, the particles, sometimes you can see the individual grains and sometimes it just looks like a powder. You can't even really see the particles. It just looks like a smooth powder. Those have different diameters. Those particles have different diameters, and there's a distribution of those diameters. Also, surface area. Think about your Brita filter. The charcoal in that Brita filter, it's got a high surface area because that's what the sticky part is. So they take charcoal, they purify it to some degree, and pulverize it so it's a powder, and then they heat it up really, really hot and burn off all of the surface molecules that will burn off. They don't combust it in oxygen. It's already been charred, so it's carbon, and then they heat it up to desorb all of the organic molecules that have stuck to it. And so now you have activated charcoal. So that's what the activated part is. Really fine particles, but it has an enormous surface area because it's very rough. So surface area is a particular property of particles that you can track. And if two powders have different surface areas, they're not the same. So you could, if you have the characteristic ability to measure surface area, you can tell the difference between powders that look the same, that have a lot of the other same properties, but they may be, the very particles themselves may be rough or smooth, and so they might have a different surface area. And then there's different morphologies. Morpho being the Greek for form, so different form or shape. You can have, crystalline or amorphous forms, or you can have rods and cones and, cylinders or spheres, and you can have some combination of that. So we'll look at these physical properties and how we analyze them today. So for sieve analysis, I brought some show and tell. So these are some sieves. Try not to get your oily fingers on the steel, but if you want, pull them around the rim. These are brass with a steel grate in them. It's a little screen, and it's exactly what you think. You just put the powder in the top, and it flows through the screen. But it's pretty difficult to get it to go through the screen. And so what would you do if you were to do this by yourself? You'd put the powder in and you would shake it, you'd tap it, you'd rotate it. That's what I call the shake, rattle, and roll. Okay, and they all have like a particle size that would pass through this screen. So this will hold everything above a certain particle size, and everything below a certain particle size will go through if it's oriented the right way. If you've got rods, they're going to sit on the screen. So you have to tap them and roll them so that the sticks go through. Okay. And so you tap, shake, roll. You can do this with wet and dry. So you can do dry sieving or wet sieving. There's a range of little machines that do this for you. This one is a Rotap machine. So the whole stack is tilted slightly and it's rolled so that the powder is rolling over itself. And then sometimes we have wet sieving, so that helps it move and keeps the dust down. And so we roll it, we spin it, and then there's a shaker, something that taps it or shakes it. And so there's shaking, there's rolling, and then there's spinning, and then sometimes there's a fluid that pushes it through. And some, it's not a complicated machine really, but still that with the motors and all of that stuff, it adds up. So it's this is a $4,000 one. And here's a little $700 one that only does 2 screens at a time. So you start with the couple of coarse screens, and what you do is you put your powder in the top screen, and you weigh out the amount of powder, typically by difference. And so you have a large container, you weigh it, and then you put a scoop of powder in there and you weigh the container and see how much you put in. So by difference, you know how much you put in. Then you give it the shake and rattle and roll, and the stuff that goes through ends up in the big bucket. And then you weigh that screen, and you now know that the percent that was captured by that screen and the percent that passed that screen. So percent passing is is one of the numbers that we track. And then you can put a couple of screens together, so it passed the more coarse screen, and then it gets to a finer screen, and you can have a stack. You see, here's one with 1, 2, 3, 4, 5, 6. The bottom one's not a screen. The bottom one's a catch pan. So they've got 6 screens right here. But in our lab, we've got like 12 different ones, but we've never really had to do particle analysis. I just have the screens. And there was a company south of here, it was an alumni. He said, hey, come down and we're clearing out this lab. We're moving our facility and we're getting rid of everything. So come grab whatever you want. So they had a whole cabinet full of these screens. And I was like, never know. Might want to do particle analysis one day. I don't have the tapper or the shaker or anything, so I'd have to do it by hand. But you can do it by hand. You're saving $4,000. So this is the data that we get. So sieve analysis for particle size distribution, you might have these really not, sort of descriptive terms like fine grained or coarse grained. And like thinking about clays, you have silt, which would be a fine grain, or coarse would be sand. And of course, even more coarse would be gravel, or even more coarse than that, big rocks like cobble. Okay. We had actually, when I worked at Pantex, we did sieve analysis on explosives, and this explosive kept failing our tests, and yet the sieve analysis said it was just like this other explosive that didn't fail the test, and we could not understand why. The distributions looked identical, and so then we were interviewing the technician, and they said, oh yeah, well, there were some pickers, is what I call them. There were some pickers in that second group. And we said, what is a picker? Well, in the top screen, there were some like big chunks, and they were picking those out. So they were skewing the analysis. These were not the same. There was actually big crystal group, things that were glopped together that they were picking out. And we're like, that was important. So whatever was causing those big crystals was something that was causing that whole explosive to fail. So you have to like pay attention to everything, including the pickers. The term picker came from when we were trying to do dredging for gold. And so we would dredge for gold, and we were always looking for pickers in the top, large chunks. We never found any. But you can see these terms of fine, medium, and coarse. Those are subjective terms. But down here, these would be the sieves that you would have. So you might have a 20 micron sieve. It'd be great if you had all of these, but think about how many pans that is. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that'd be a stack of 10 sieves, coarse all the way down to fine. And so when you weigh them, you weigh all of those, and it's going to add up to 100% of the weight that you put in the top. Okay, if you captured everything. So that's why this is done on a fraction of total sample scale. So you can kind of see up here at the top, we've got 100% of what you put in the top. So let's talk about this silty thing here. So you got on this one, nothing on these top 1, 2, 3, 4, 5, 6, nothing on these top 7. So these all had no mass to speak of captured by those. And so it passed all of those. And then on the 0.6 one, it was right here. So let me erase that first little point. And then on the 0.02, it was here. And on the 0.006, it was here. And on the 0.002, it was here. So you add up the weight, the extra weight on all of those, and you end up getting to 100. Notice how that's different than sand. Here, all of that weight, of course, I don't know with these screens down here how they got this curve, because they really only have 2 data points, right? They've got all the mass on the 0.6 and the 0.2, and there's a little bit, 10% passed through the 0.6, and maybe ended up, on this next one. Since it drops down to 0, they probably had some mass down here on that one. So you had 3 screens that had mass. So when you have all your mass on only 3 screens, the particle size distribution is really sharp. If you were to take the derivative of this cumulative distribution, it would look like this. It would come up here, and the maximum would be around 50%, and it would come back down like that. So that is your probability of finding a particle of any of those masses. It's like a Gaussian curve. Well, it's not necessarily Gaussian because these could be skewed, but that's your. So these cumulative percents are just the integral of the Gaussian curves, or the frequency curves. Now the very top number on this curve here is the mode, right? So we remember that from we were doing the statistics. And let's look at this one. This clay, I don't know why there's an extra EY, but clay with gravel and sand. We've got a peak here. You see where it gets steep? That's where you have a peak. So this is a peak right here. And then it gets steep again over here. So you got a peak there. So there would be a peak like this, and a peak down here like this. And this would be bimodal. You've got two peaks. You've got two maximum of those two peaks. And so those are called modes. So that would be a bimodal distribution. And that's what we see on this dashed line here. The forensic application is if you plot this out for two different powders, you can see if they're similar or different. And so this is how you would track the physical properties of a powder to see if they're similar or different. So you got two baggies, chemically, same amount of cocaine. Let's look at the particle size distribution. One appears to be a little more coarse than the other, but appears to be maybe subjective. Maybe you're just looking at it differently. Put it in the sieve analysis or some other kind of analysis and see what the size distribution is, or maybe it's a different morphology. This one has needles, this one doesn't. You know, so you can track the physical differences and tell the differences between evidence. Here's some other things that are not so tedious in terms of their analyses. You can use laser diffraction or light scattering for particle size distribution. So here the particles flow through a laser beam and deflect that laser beam. So these are the little particles. They give off diffraction patterns, and you've got detectors on there, and they scatter the light. And so here's a bimodal distribution. So you've got a mode here, and you've got a mode here, and it's showing the cumulative distribution in gray. And you see where the steep parts are, that's where the maximum of those peaks are. So here's a steep part right here, so that's where the maximum of that peak is. And you can have this one that's like the 10% diameter, and there's a 50% diameter, and there's a 90% diameter. So those are some terms that you can use, you can report. You can also report like the average diameter of this group and the average diameter of this group. Now this is nice because you don't have to have sieves. You're not doing anything gravimetrically. You're looking at the volume of that particle in solution as it passes through the light beam. Here's a cool one. So this is a little electric cell with salt water or some conductive solution in here. And then you're passing the particles through this little hole, and you're creating a resistance in the liquid. So the electricity is passing through the liquid. When a particle passes through that hole, it disrupts the electricity a little bit, and the resistance of the cell changes. So this is called electrozoning, particle counting. You can count particles, and the effective diameter of that particle in the solution changes the signal. And so you can have an effective diameter of those particles. This one, and neither can the previous one, these can't really tell the morphology of the particle. So you're getting an effective diameter of a spherical particle. So you're losing the shape of the particle. And, a rod is not going to have, a rod's not a sphere, but it'll behave like a sphere that has some intermediate diameter. It's not the diameter of the rod, it's not the length of the rod, it's something in between, an equivalent sphere of that rod. And then here's dynamic image analysis. So this is a little cascade of particles. It can be dry or wet, which is kind of interesting. So up here you have a little shaker table. You put your powder on it, and that table shakes. I don't know how to draw shaking, but there it's shaking. and it flows over this little waterfall, or not really, but it falls over the lip and goes in front of the camera. And when it goes in front of the camera, you got a really fast camera, and it's just taking pictures. Pop, 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 pop. It's not a video; it's individual frames. So the computer will track. It'll take so fast that you might have a particle that the computer tracks, and then it'll take another picture where that particle is at the bottom, and it'll make sure that it has like one picture of each of the frames as the particles pass in front. And then the computer identifies, and it's always a high contrast image, like bright white background and shadowed particles. So these black particles are falling in front of the camera, and the computer can quickly identify their edges, and it can sort of look at their outline, and it can calculate the size of the particles. So this can do 10,000 particles a minute or faster, and that's good, because then you start getting statistically significant populations of particles. So let's talk about how particles are made. You know, particles are typically recrystallized or crash out of solution. So they're surrounded by solvent of some sort. And then there's nucleation. So the solute, for whatever reason, becomes too concentrated for the solution, and they find each other and they associate. And so these two particles snap together, and we've got two new microcrystals that are just like dimers, and then trimers and tetramers and so on, and they start to grow. So this nucleation of new crystals, and then you have growth of existing crystals. And they can grow in different ways. They can grow side by side, end to end, top to bottom. So there's all different ways that they can grow. And there's always this competition between growth and nucleation. So when we precipitate out something that precipitates rapidly, we get really small crystals, because nucleation is favored. If something is really insoluble, think of like, did y'all do precipitates in Gen Chem ever? What was it? Did you do like silver chloride? Or a lot of schools will have a silver chloride lab where you do gravimetric analysis of silver chloride. So you have chloride in drinking water or something, and you add in silver nitrate, and it crashes out the silver chloride. And silver's nice and heavy, so you get a big signal of mass for a small precipitate. Does that sound familiar? Yeah. And you got to dry it so it weighs accurately, because you got to get rid of all the water weight. Oh. Okay, with copper.
Yeah, they dissolve copper.
Yeah, so the silver chloride really is insoluble in water. I mean, it's dramatically insoluble. So the very first drop you put in, nucleation is huge. I mean, it's silver. It forms so many little microcrystals that powder is really, really fine. But if something's kind of soluble, it's going to precipitate out slower. And what does slow mean? Slow means growth. So you have fewer nucleations, and there's time for those crystals to grow. And this is how you make really good crystals, actually. You put a seed crystal in there, and you don't disturb the flask at all, and you let it grow. Now, if you ever get a chance, look up, there's no recipe, really. You just put a whole bunch of sugar, like a cup of sugar in a cup of water, or maybe 2 cups of sugar in a cup of water, and you boil the water so it goes into solution, and then you set it aside to let it cool. If you can suspend the tip of a toothpick in there, you can make rock candy. Like make a giant, perfect, beautiful crystal of sugar. Okay. I think the Chem Club flyer in the other room has a little pipe cleaner, and they stuck that in the water, and he has little crystals all around it. And they made it look like a little gingerbread man, and he's covered in sugar crystals. So that's favoring growth over nucleation. So we have the little deformity. The reason the wood works really well, because it has it's like a sugar. It's not exactly sugar, but it's a carbohydrate. And so the sugar molecules will latch onto that wood and grow from there. So that's trying to favor growth over nucleation. Why does scratching the side of the flask cause nucleation? Have you all ever done that when you're trying to get a precipitate to crash out of solution? You scratch the flask. That vibration is enough to get two of these to get close enough to each other. Fantastic. We got a little, that's like a pinball machine. So, vibration of the solution can cause these two solvent molecules to bump out of the way temporarily, and have another one of these molecules stick. So if there's no vibration, these slip past each other and they don't crash out unless they're extremely insoluble. So if they're mostly soluble, you've cooled the solution down, you want to start precipitation, you agitate it in some way, you form nucleations, you get new crystals. If you keep scratching, you keep favoring nucleation, and so you get a lot of fine crystals. If you just scratch enough to get it started and let go, then you start to grow longer crystals that are easier to filter. Wish you had known this before organic, right? So then solvent effect on crystal morphology is a research project that I did. My research is in solvents, and so once a microcrystal is formed, you've still got solvents around the outside. And if the solvents are attracted to like A versus B, every crystal has a different functional group of the molecule pointing out at it. And so like A may be hydrogen bonding faces and B may be pi stack faces like the aromatic rings. And so those are two different kinds of intermolecular attractions. And so if your solvent favors B, then it's real sticky to B and A grows because it doesn't like A. So it's sort of stabilizing the B face and A grows. If your solvent likes A, then it stabilizes those sides and B grows because it's easy to move the solvent out of the way on the B face and you just grow the crystal that way. And if it doesn't really have a preference, then the crystal can grow in all dimensions. So this was the theory that I had, and I had seen an article. It wasn't an academic journal, but it was in a book, Formulation Chemistry. And I got to thinking, wonder if I could do that with the Hansen solubility parameters. In other words, I could take a molecule like nitroaniline, find its Hansen solubility parameters, and then put it into different solvents and see if I could change the shape of the crystals that come out. So that's what this research is about. So I'm going to go quickly through the Hansen solubility part. But what we wanted to do is see if we could change the crystal morphology by changing the solvent. So this is the molecule that we used, 2, 3, and 4 nitroaniline. And this is how we did it. We weighed out 0.2 grams into a vial. We added the solvent dropwise and measured the mass that we added. And then we could look at it and see if we saw any crystals. And when we didn't see any more crystals, then we had a sort of almost saturated solution. And we could determine, in this case, like ethyl acetate, very little ethyl acetate was needed to dissolve it, whereas isopropanol, we needed, 10 times more to dissolve it. And so that meant this molecule was more like ethyl acetate than it was like isopropyl alcohol. We did this for all 3 of those compounds. So we came up with the Hansen solubility parameters. I'm not going to go through all of this, but this is how we can find the nature of this molecule in terms of where it fits in 3D space. So this is 4-nitroaniline, and all the solvents inside this sphere are good solvents for that. So it can essentially dissolve. It's like miscible with those solvents. All the solvents outside that sphere are what you would consider bad solvents. So you can't really get that molecule to go into toluene or hexane. Or water. Water's way up above. This is a hydrogen bonding axis here. So this one is H. This is the polar axis going back, and this is dispersion or the flexibility of the pi cloud around the molecule. So you can see hexane, it doesn't have any polarity, doesn't have any hydrogen bonding capability, and it's got this amount of dispersion. Toluene, it has an aromatic ring. Bigger, flexible, more flexible electron cloud, and so it's way out here on the dispersion axis. And the difference between the methyl group and the aromatic ring gives it a little bit of a dipole moment and a little bit of a hydrogen bonding capability. Not much at all. Water on this scale is way up here at the top. Okay. So what we want to know is, can I take 4-nitroaniline in a good solvent like NMP, okay? And what if I came out of this sphere into a bad solvent? I will have taken all the molecules around the 4-nitroaniline and replaced them with a bad solvent, and it's going to want to nucleate and form a crystal. What if I then came out of this sphere this way and went to hexane? Now I'm changing the molecules around the outside of that solute, and maybe I change the type of crystal it makes. And that's what happened. So this was really cool. So going through all of this, I want to get to the pictures. Oh yeah, well, talking about blend, yeah, never mind. That's a fun picture. Yeah. So this software right here will calculate the blends that will dissolve your substance, okay? And they go from 1, 2, and 3 component blends. But I wanted to do the 4 component blend, and so we wrote our own software. So that's my little brag picture. Like we wrote our own 4 component blend optimizer. So teamed up with Brian Loft in the math department. So this is how we do it. We create a saturated solution of the molecule. We mix 1 part of that saturated solution into 9 parts of a non-solvent. And then we stir, and then we mix it into water. And we get lots of crystals. So this is what we ended up with. So we take path 1, crash directly into water. That's our reference crystal set. The other path is to go into a different solvent, a non-solvent, and then crash that into water. So we're going 2 different routes, and we're comparing everything to the water crystals. And so here's our setup, super easy, okay? So here's our molecules dissolved in ethanol, and then we take 1 mil of that and put it into 9 mils of water. We see it crash out, okay? Then we filter it, and then we repeat. So we did all those different experiments, and then we analyzed them under a microscope, and that was the real tedious part. So we didn't have a particle counter. We didn't have the sieves yet. We didn't really have enough precipitate to use these sieves, because the precipitate would be like the captain and this would be like the Titanic. You can't measure the captain's weight by taking him on and off the Titanic. It's just, he's down in the noise, okay? But we could do microscopic analysis. So these are pictures of the various water crystals. So when we went straight out to water, here's water up here. This is the kind of crystals we got. Definitely bimodal. We have some small crystals and some larger crystals. So we have some of these longer crystals here, and then we have some smaller ones. This is under cross polarization, so we have a dark background, and you can see that's what the water crystals look like. This is going into methanol and then into water, and we've got some different looking crystals. Our crystals look more pure, they're flatter, they have a smoother surface, and they're less bimodal. We can look at going out of the sphere over to ethanol and then to water, similar to methanol. Now dramatic, we go out to acetonitrile. So we have our molecule dissolved, we add it into 9 mils of acetonitrile, and so we've come out of that sphere and we're 90% the way over to acetonitrile. Completely different solvent cage around the molecule, and it hasn't precipitated yet. We've just exchanged the outer molecules, and then we go into water and we get nucleation, but we might have molecules that stabilize a different phase. Our needles are thinner, and they're still clean. They have clean, smooth surfaces. Then we went into acetone, and we got plates. So we got more of these plate-like molecules. So we're definitely stabilizing one face and letting 2 other faces of the crystal grow. And then here we go into dimethylformamide. Our crystal surfaces are rougher, and we get a lot more gravel and conglomerates. And so this is, it seems like we're favoring more nucleation than growth. And these are crystals that have nucleated, and then the crystals stick to each other. And then this is toluene. It hated toluene. So we went into toluene, it started precipitating immediately. And we see gravel pretty much. So we went into toluene and then went into water, and it's not plates, it's not needles, it's gravel. So this is showing you, now what's the forensics application? You've got people in clandestine drug labs and maybe even state-sponsored drug labs that are going to use different solvents. And you can see here, same substance, different solvents, totally different particle characteristics. And so you can learn something by looking at the images of the particles and say, these are not from the same process, or they're consistent with the same process. I can't say for sure they're the same process, but I saw nothing that would say that these 2 powders came from a different process. And this, I had a picker. So I saw on the toluene when this piece right here, and that long needle-like crystal did not grow in the solution. It grew on the glass container. So the container can be important in some of these situations, that things can grow on the surface of the container because the container has intermolecular forces too. And so this powder, when I put it into the beaker, crashed out of solution and some of the crystals grew on the surface. And then here's 4-nitroaniline into propylene carbonate, which is out the back of the sphere. And it's also rapid nucleation, very little growth, a lot of gravel. So here's all of the different shapes that we got from the same substance going into water. But there was an intermediate solvent on all of these. And you can see a pretty dramatic difference in the different crystal morphologies. Now, what about their size distribution and length to width ratios? Well, this is image analysis. You get in there with a microscope, drag the mouse, measure the things, write it down. What a tedious thing, okay? But that's what you have to do unless you can train a computer to do it. Image J will do it for you, but you can't have any overlapping particles. So it's pretty tedious. And so that's why my error bars are so big, okay? And so I couldn't really see a trend in the polar component of the solvent or the dispersion component of the solvent, but there was a possible trend in the hydrogen bonding portion of the solvent. And then here's my cumulative distributions. So you can see that the gravel particles, it was all small particles, okay? So we got to the 100% of the particles before we had all of these length to width ratios were really small, and then the ones that had some particles with long needles, down here the length to width ratio was 10 or more, and then a lot of particles where they were almost spherical. So just showing you that you can do the analysis and look to see, yeah, we have distinct differences in these different powders. Okay. Now, you can also look at the top 3 particles, and you were able to pick out a different trend by looking at the top 3 particles. Still based on the Hansen solubility parameter, the H hydrogen bonding component. And then here's the apparent size distribution, looking at that cross-sectional area. Also, you can really tell, compared to water, water had the smallest cross-sectional area. Rapid nucleation. 4-nitroaniline is not soluble in water at all, so when you dump it into water, everything crashes out. Lots of nucleation, very little growth. Every other intermediate solvent allowed growth to go for a little bit longer, and some of them allowed it to go for quite a while, like acetonitrile. We got a lot longer crystals with a lot more surface area in going into that particular solvent. So the crystal morphology of this particular substance appears to correlate with the hydrogen bonding parameter. And then my point for the forensic utility is that you can really tell the difference between how substances were prepared by looking at the particle physical properties, size distribution, surface area distribution, and morphology like length to width ratios, rods, needles, plates, spheres, etc. Now, my issues with my analysis, I was doing this by hand, so I only had about 200 particles that I could stand analyzing before I got crossways. And it's better to have 10 to 20,000 particles for each sample. So I can't say that these conclusions are rock solid, but we saw trends with just 200 particles per system. Okay. And these are the students that did the work, helped me with the analysis. Each one of them analyzed, hundreds of images. So that was good. And they're all in, let's see, Katie got her PhD at A&M. Derek is went to industry in Pennsylvania. John worked for Baker Hughes. Carl went to GE, oil and gas. And Steve, I've lost track of. I think he might have gone into Baker Hughes also, but I'm not sure. But yeah, that was great. Good work. So that's all I have. And I'll take questions on homework, or y'all are free to go.